Okay, so this particular problem is basically asking us, what does the second derivative mean? Now, the question basically says, you consider this particular function, what can we tell from the second derivative? And that's the basic idea. And we're given some options here. I'm going to rearrange these options a little bit and group them into three separate groups. The first is gradients, the second is functions, and the third is the point of inflection. And basically what I'm doing here is I'm saying, does the second derivative describe the gradient? Does it describe the function? And or does it describe the point of inflection? It could be any one of these, combination of these options. So let's start by looking at whether how the second derivative describes gradients. Now you might recall that gradients are very similar or almost equivalent to first derivatives. They're not exactly the same thing though, and I'll upload a separate video explaining the relationships between terms like gradients and tangents and first derivatives, but I don't want to go off topic, so we'll just say that in this case we can say that the gradients are equivalent to first derivatives and vice versa. So if you come back to the question now, eliminate the word gradient and basically replace it with the word first derivative, and they're basically the same thing. So we're stuck with these three options. Is the first derivative decreasing or increasing, or is it constant? Okay. Now remember from a previous video that we can figure out if something or how something is changing by taking the derivative of that something. Okay? So for instance, if we take the derivative of our function and we get the first derivative, that's this here, and this expression 4x minus 3, this describes how the function changes. And I might upload a separate video again just to explain how this works and why this works, but again, don't want to go off topic, so we'll just say that the first derivative here describes how the function changes. So coming back, we know that the first derivative describes how the function changes. How do you think the second derivative, or what do you think the second derivative would describe? Maybe pause the video and take a second to think about that. See if you can come up with the answer. Well, logically, the second derivative would tell us how the first derivative changes. And just a while ago, we saw that the first derivative and the gradient are equivalent. So, coming back to our question here, we can find the second derivative, and I think you've already done that for this particular function, and we found that the second derivative was 4. It was a positive number, was positive 4. So that means we know that the change in the gradient, or the change in the first derivative, is positive 4. Okay, but now take a moment to think, and this relates back to the options we have for the answers for this question. Take a moment to think, what does it mean if something is changing by a positive number? Does it increase? Do you think it'll be increasing or decreasing? Well, you know now that the gradient would be increasing. So this helps us narrow down our options a bit, but there's one other thing we need to look at, and that's the phrase constant rate. So first, let's think, what does it mean if something increases by a constant rate? For instance, if you're in a car and you increase your speed at a constant rate. Let's say you start off at a speed of 10 and you increase it by 4 every second or every minute or something like that. Then every second, for instance, you start off at 10, then go up to 14, and then 18, and then 22, and so on. So what this means is that the rate at which you're increasing your speed, that rate is constant. Now in this case, the second derivative was the number 4. Now that's a constant. And we know the second derivative tells us how the gradient changes, and we know in this case it increases. And now we know that every time the gradient increases, it would increase by a constant number. By a constant number, in this case it's 4. In other words, the gradient changes at a constant rate. And that's why we can confidently choose this particular option as being one of the correct answers. We're just going to quickly look at what the second derivative, what would it mean if the second derivative was something else? So what if the second derivative was a negative number? Previously you saw it was a positive 4, positive number. What would it mean if it was negative? Take a minute to think about that, and you can pause the video. Well, that would mean that the gradient is decreasing. Now what if the second derivative was 0? Not positive, not negative, not a number, 0. It is a number, but it's 0. What would that mean? In that case, the gradient would be constant, which means that the gradient itself is not changing. And why can we say that? Well, we know that the second derivative tells us about the change in the gradient. If the second derivative is 0, it means that the change in the gradient is also 0, which means that the gradient isn't changing at all. Now what if the second derivative was something like this equation? This one's a bit trickier because you have an equation with a variable x. And basically I'll tell you what this means is that the gradient, the change in the gradient itself is also changing. Now before I continue, I just want to remind you that this is something I totally made up. All the values are made up, so don't wonder like, where did I get this equation, where did I get these values? Okay, I was just saying that the second derivative is this equation, so let's plug in some values for x, and we can calculate the second derivative just by plugging in values for x like so. That's how we get these values here. And we can also calculate values for the gradient using the equation for the gradient. Again, don't worry about where I got it. I'm just telling you these are the values. What's more important to notice is that as the values of x are increasing, so are the values for the second derivative, and so are the values for the gradient, but the increase in the gradient with each step is itself increasing. So the rate at which the gradient is changing is also changing, and in this case it's also increasing.
That's all, folks.